All right, so I've broken this video up into two different parts so you can watch them and kind of consume them separately if you'd like. So back to what we were talking about. Membranes. Boom, boom. There. Yeah. Um, Membranes. We introduced them the other day. Um, the different roles that they play or what a membrane is involved in. Now, I'm happy that I brought up molecules like glycerophospholipids and sphingolipids because this is particularly important to them. Now, here what we have is a depiction of lipid mobility. And basically, if we highlight and look at the head group that is blue, that just denotes a single glycerophospholipid, single sphingolipid. Now, they can move laterally, shown in depicted in B, very quickly. So if a lipid that stays on one side of the leaflet, it can move, from place to place very quickly. However, to go from the inner leaflet to the outer leaflet or the outer leaflet to inner leaflet, that's going to happen very slowly. Now, in order for that to happen at a little bit more of a rapid pace, there are some enzymes involved in that. And to get an appreciation for that, we've got to know kind of what a lipid bilayer looks like in under different circumstances. Now, heat produces motion of all of these lipids. So if you imagine a lipid in its what's known as its fluid state, or it's basically more mobile state, you're looking at and kind of imagining a lipid bilayer or a membrane of a living organism. You're looking kind of at the bottom one as a good rendering of that or a good depiction of that. However, at a depleted temperature, a lower temperature, then you have this paracrystalline state. So it's a gel-like state, in which case it's a little bit easier to decipher the different components of the leaflets and everything like that. Now, we have a transition temperature where a lipid is going to go from a bilayer to a gel-like solid. Above a transition temperature it would be in its liquid crystal or its fluid state, whereas below that it's going to be in the paracrystalline state. Now, the transition temperature is dependent on the chain length and the degree of saturation of the component fatty acid residues. Now, think about this with respect to what we were talking about a few days ago and the E. coli growth. So, E. coli, when it grows, if it's growing at 10 degrees or at 40 degrees, the length of those lipids is going to influence or is going to be influenced by the temperature. So if you can imagine those lipids that were grown at 10 degrees, or sorry, those E. coli that were grown at 10 degrees versus at 40 degrees. At 10 degrees, you had a larger number of unsaturated fatty acids. At a higher temperature, you had a higher number of saturated fatty acids. And those two things, like you could almost think about it as the number of saturated fatty acids increased, the number of unsaturated fatty acids decreased, and vice versa. Because what we were trying to do is basically get a membrane that has a kind of uniform composition, regardless of if you're growing at 10 degrees or if you're growing at 40 degrees. You want it to be equally, in uniform composition being like equally fluid, equally as rigid. And so the fatty acids that are produced by that E. coli or whatever organism is going to vary a little bit. So, to think about that in terms of uh, other organisms, um, polar bears, for instance, they're going to have a different, or membranes of polar bears are going to have a different fatty acid composition than, say, let's go with, I don't know. I don't know what the state bird of Florida is. We'll go with Texas. Texas is warmer than where polar bears live. So a mockingbird. I would imagine that if you did a plasma membrane analysis of any muscle tissue of a polar bear versus a mockingbird, you're going to see a little bit of a difference in terms of the fatty acid chain length. I would imagine that your polar bears would have a higher percentage of unsaturated fatty acids in their membranes, whereas mockingbirds are going to have a greater percentage of saturated fatty acids because those saturated fatty acids are going to be a little bit more rigid. So now cholesterol is one variable that is important to think about. Cholesterol is going to broaden the range of that phase transition. Now, when we look at this figure right here, one thing that's really important to remember is that um, bacteria don't have cholesterol. So they are really reliant on varying the percentage of unsaturated fatty acids to saturated fatty acids. And again, to highlight this graphic right here, what you really need to do is understand myristic acid and palmitic acid are your saturated fatty acids, and they are in greater abundance at higher temperatures. If we were to compare that to palmitoleic acid and oleic acid, those are both monounsaturated fatty acids. And at 10 degrees Celsius, you're going to have almost, let's see, that would be 64% of your fatty acids are palmitoleic oleic acid of your membranes. So your membrane composition is going to be different based on the temperature that E. coli is grown at. And I would imagine for other organisms as well. Okay, now when we move forward here, as I've talked previously in this lecture about your inner and your outer leaflet, the composition and distribution of different types of lipids is going to vary. Um, Total phospholipid, you've got an equal distribution of your fatty acids, or your, sorry, you have a the kind of density and abundance of total fatty acids on your inner leaflet versus your outer leaflet. They're going to be the same. You know, if you imagine that you have 100 fatty acids or 100 glycerophospholipids and sphingolipids that make up the outer leaflet, you're going to have 100 that make up the inner leaflet. Now, the composition of the inner leaflet versus the outer leaflet is going to vary a little bit. This is kind of what this is showing is basically in an unstressed environment. In the outer leaflet, what do you have more of? You have more sphingomyelins and phosphatidylcholine. On your outer leaflet, do you have any phosphatidylserine? Well, in an unstressed environment, no, you don't. Whereas in your inner leaflet, you've got a higher percentage of phosphatidylethanolamine and phosphatidylserine. Now, these things will change depending on the conditions that this organism is in. And in order for that to change, well, in order for what's in the outer leaflet to become a part of the inner leaflet, or the inner leaflet stuff to become a part of the outer leaflet, well, what we need to do is we need to kind of make some changes for that. Phospholipids are synthesized on or near the interior of the membrane. So they're synthesized basically at the inner leaflet. Now, there are two mechanisms to get phospholipids from one side to the other. One is to use an enzyme or a class of enzymes, which I just love this name, flipases. Flipases are enzymes that help move a lipid from one leaflet, the inner leaflet, to the outer leaflet. And here what we have in the middle is an example of a flipase in action. That flipase is going to help move that substance or that lipid from the inner leaflet to the outer leaflet. Now, um, can that action take place without the influence of an enzyme? Absolutely, but it's going to go extremely slowly. Now, that lateral movement, something staying on the same side or the same leaflet, that's going to happen very rapidly. Now, flipases, typically what they're going to do is they're going to help the membrane kind of reach an equilibrium in terms of the distribution of the different components. So basically, and this equilibrium is not an equal number. It's not to say, oh, well, if there's 25 phosphatidylserines on the inner leaflet, then we got to get 25 on the outer. Instead, there's going to be a ratio, and that's going to be dependent on the conditions. So phospholipid translocases transport specific phospholipids across a bilayer in a process that is driven by the hydrolysis of ATP. Now, what I want you to be familiar with is I want you to be familiar with these guys, flipases. They like to manage an equilibrium. Translocases can establish a non-equilibrium distribution of a phospholipid. Now, membrane composition. What are the components of a membrane? From organism to organism, this is going to vary. The same things that make up a human membrane are going to differ from what make up an E. coli membrane, a liver cell membrane versus a brain cell membrane. We're going to see all this variation there. Now, biological membranes contain proteins and lipids as your major components. The proteins catalyze reactions, mediate the flux of nutrients and waste, and participate in relaying external information to the cell. Now, protein to lipid ratios vary with their membrane function. So here what we have is, let's look at a mouse or a human myelin sheath cell. We've got some proteins, phospholipids, and sterols. Um, Mouse liver cells versus a maize leaf. Well, you're going to have higher percentages of proteins, but mouse liver cells are going to have higher cholesterol levels. Yeast and paramecium, well, they're going to have relatively low percentages of sterols. And then if we look at E. coli, well, E. coli has no sterols. Um, so what I want you to take away from this is that the major components of a membrane are your lipids and your proteins. There are other things that help with that fluidity and flexibility of them, cholesterol being one of them, or sterols and steroids being one of them, cholesterol being a major mediator of membrane structure. Now, what cholesterol is going to do is typically it's going to make a membrane a little bit more rigid, um, which is one reason why, if you think about somebody getting a annual physical exam, um, their cholesterol level is going to be monitored. And if their cholesterol level is too high, their blood cholesterol level is too high, that could be an indication that they maybe are at risk to a cardiovascular event like a heart attack or a stroke or something like that. Um, and so I'm going to go ahead and stop right there. And I hope that you guys have a great day. And that's it. See ya.